Good morning to all. Myself P. Loganathan. Today's topic we are going to discuss calculation of photovoltaic system size for a residential building. First we prepare a building plan which contain the information of building area, how many floors, how many rooms and what are the sources and what are the loads. So you are looking here the building approximately 2000 square meter area and double floor, 3 rooms, and sources are solar panel, battery, inverter, net metering and grid. Then loads are TV, fridge, washing machine, air conditioner and all kind of electrical appliances for our daily requirement. From this building plan we can calculate PV system size by using 4 different steps. That is, one step, calculate daily and annual electrical energy demand. Step 2, calculate daily and annual sun hour. Step 3, calculate PV system size. And step 4, select the panel size and number of panels. Now going to the next slide, you are looking the table here. Step 1, calculate daily and annual electrical energy demand. So first we consider the building is already existing or newly designed. The building already existing building mean first we collect the previous 12 months of electricity bill. Through this electricity bill you will take a sum of annual energy demand, or energy audit report you have in the existing building, you collect the annual energy demand through the energy audit report. Unless this is a new building, hereafter only you are going to fitting the electrical appliance for our daily requirement. You listed the appliances what we are going to use for a day-to-day usage. So you listed the appliances and calculate the how many quantities we need and consumption of energy during the time of operation. That is a consumed energy. What is the energy rating for the time of operation and how many hours it's going to work in a day. Then what is the total amount of energy consumed per day. So this is a basic information, and develop the table up to for a annual energy demand. To calculate annual energy demand, how many days you are going to use over the year and what is the total amount of energy consumption. Like that, the table you are prepared carefully with the requirement of electrical appliance for our day-to-day usage. Then you calculate the formula for a daily electrical energy is number of load multiply with the number of hour and multiply with energy consumed by the load. So number of load is nothing but our electrical appliances, and the number of hour, how many hours going to operate over the day, and energy consumed by the load during the time of operation, how much of energy consumed by the appliances. So this is a way calculate the daily energy demand. For example, you consider one fluorescent lamp which is have 60 watt of energy. So per day it operate 2 hours. So 2 hours into 60 watt, 120 watt is a per day energy demand by the lamp only. So like that you prepare the electrical appliances from the lamp to fridge, washing machine and all kind of day-to-day electrical usage requirement for our convenient. So this is a daily energy demand calculation method. Through this method we are calculate 50.81 kilowatt hour is a daily energy demand. Then annual energy demand is total energy consumed by per day multiply with the number of days, you can calculate the annual energy demand. Here what is the difficulties? All electrical appliances per day we are use different hours and different timing. Like that all over the 365 days of year it is not constant or same for the time of operation and number of hours. So individual calculation is very important for a annual energy demand, because of every appliances is operated under various timing, various hour and varies the period of working. So this point of view, you carefully listed the electrical appliances and calculate the annual energy demand. Here we calculate annual energy demand is 11,845 kilowatt hour. Generally, the international standard is prescribed for a domestic or residential buildings. Annual energy demand is 12,000 kilowatt hour. Here we are estimated 11,845 kilowatt hour. So this is a very basic data. From this data we can develop the further energy calculations. So step 2, calculate daily and annual sun hour. This annual sun hour is consider some graphical assumptions that we are discussed here. So first one, what is sun hour? So sun hour is nothing but per day from morning 6 to evening 6, the sun is produce the rays on the surface. So that hour is called sun hour. Here the solar panel is designed by a crystalline structure which have a photon within the structure itself. When it absorbs the heat from sun, it emits the photon and induce the electron at the output. So heat energy is converted to electrical energy. That is a solar principle. Now the solar, how many hours working over a day, that one is a major important thing. That one is calculated by the sun hour. Here why this kind of assumption we are calculated? First thing, the all over the day the temperature and atmospheric pressure is not constant from the morning to evening. For every hour to hour, time to time, it will be varying, not a constant, because of atmospheric pressure and temperature and all kind of obstacles in the surrounding of the earth surface. For example, that example is consider hill station have a different climate and atmospheric pressure. The same is different in the ground surface compared with the sea level. So through this way, that standard conditions are prescribed by international standard. So that is calculate the sun hour for standard test condition. So through this standard test condition, 1000 watt per meter square at 25 degrees Celsius with air mass 1.5. So 1000 watt is a protection rate, per meter square is nothing but area, at 25 degrees Celsius is the nominal temperature with air mass is 1.5. So this is a condition the solar is produce the output at area. So in these conditions the geographical map is designed through the graphical assumptions. So you are looking here, the graph start from light green color to dark brown color. So this is represent that a different period of working solar hour, that is sun hour, which means the sun focused rays over a surface, the area of the different locations, geographical locations is varying. For example, 3.2 here is Gauhati. So the 3.2 is a maximum sun hour over the day of 12 hours from morning 6 to evening 6. It extend up to 6 hours per day is our graphical of India position. For our Tamilnadu, per day 4.4 hour is a nominal working hour of sun through the surface of the earth surface. So total 1607 is the annual total of the sun hour. That is nothing but the sun is projected rays over the surface of earth is 4.4 hours to our Tamilnadu. So per day from morning 6 to evening 6, totally 4.4 hours only is a average sun hour for a solar. So the solar operate 4.4 hours. Within the 4.4 hours, it is able to generate the electricity. That is a concept of sun hour. So for our Tamilnadu, we calculate number of sun hours per day is 4.4 hours and the number of sun hours per annual is 1607. That means what is the per day value? You are multiply with 365 days, you can get that 1607 hours. From this two data, we are going to calculate system size. So calculate the system size is considered, first one is annual energy demand and annual sun hour and efficiency. So annual energy demand, from the table 1 we are calculate and collect the value. Annual sun hour, previous geographical map as per standard test conditions, we collect one. The third one is efficiency. So efficiency's general formula is output power by input power. The output power is based on the input. Input is considered the two different factors. One is a crystal structure, that is based on the manufacturer's company, and another one is mechanical issues. Mechanical issues nothing but the fitting of panel and wiring, power loss, dust, temperature variations. So the mechanically fitting the area based on the rooftop or ground building, the tilted angle is almost constant for a residential building. So during this case, the tilted is improper setting or light erection or correction is there, it will affect the protection rate. Then wiring, when tapping the solar panel to battery to inverter to load, the wiring is have some losses. And power loss. Power loss is nothing but the solar produces the DC converted to AC through the inverter. The conversion also considers some losses. Dust is nothing but the surrounding atmosphere provide a various dust and soils. So these are focused and coating on the surface of solar panel which affect the solar rays, that means sun rays strike on the panel. So due to this condition, the production rate is varying, and the temperature variation is expressed as a climate variations depend on the four different conditions, that is the winter season, summer season, rainy season, spring season. So the cloudy conditions and winter and spring seasons, the temperature variations affect the solar productions. So these factors affect the solar. The total system consider minimum 15% of losses and the system achieve the efficiency up to 85%. So 80 to 85% is a maximum efficiency of a system size. Here the system size is individual and module size is individual. So these three data you are collect and calculate the system size. Now going to calculate PV system size is equal to annual energy demand divided by total sun hour. You are take one value, that value is 7.370 kilowatt hour. You are divide with the efficiency of 80%, 0.8. You can get that 9.2125 kilowatt hour or 9212 watt hour. That is the system capacity is 9.212 kilowatt hour. From this table we select the panel and number of panels. So you are looking here, first you understand what is panel. Panel is nothing but the array connected in the sequence of order, which may be series or parallel. What is array? A single PV cell connected in the sequence, that is called array. So you are looking here, there are two different kind of photovoltaic cell. So designed by manufacturers, one is a monocrystalline structure and another one is a polycrystalline structure. Monocrystalline structure is nothing but a single cell is cut in the edge and joined with the panel wafers. That is a monocrystalline structure. Polycrystalline structure is nothing but the same thing, the edge cutting is not cutting the earth surface and joint melt with the neighbor wafers. So this is the arrangement for a monocrystalline and polycrystalline. So this is a basic information for a select the panel size. Now as per the standard test conditions, the solar panel is considered the some working parameters in the time of operation. is consider that maximum power rating is a output of the panel, that is 232 watt. The different companies different rating is available. For example, we are choose here 232 watt is a basic. Then operating voltage is 30.1, operating current is 7.7, open circuit voltage is 37.1, and short circuit current 8.2, efficiency is 14.2, width is 11,100 millimeter, length is 14, that means 1470 millimeter. So this is the basic information about the solar panel. When you are purchase a panel, this is a very important structures of specifications to explain the panel's behavior of the output. So this is an important step. You calculate the panel output. If failed in this assumption, the total system capacity and annual energy demand, everything is mismatched, and that you are going to wrong installation. So here looking that the output power is represent here maximum power rating. So this is our target. We can calculate the output by using two different way. First one is you are multiply with operating voltage into operating current, that is a 30.1 into 7.7, you can get that 232 of the output. And another one way you are calculate through the efficiency matching, then you can calculate the output power. Now look at that here model efficiency, consider that power output by power input. The output power is nothing but panel power and panel area. So panel power is represent here 232 as per the calculation model power, and the area is 1470 mm into 1100 mm. You are calculate that 1.62 meter square. So the total output is calculated 143 watt per meter square. Through the panel output, you calculate the model efficiency. So you are looking here output by input power. So that 14.3 is a efficiency. You are looking here 14.2. Through this data, you calculate the number of panels selections. So the basic formula PV system power divided by model power. So PV system power is 9212 watt hour. You are calculating the previous of system size step 3. 232 watt hour is specifications from the manufacturers. So you are divide that, you can get 39 panels approximately. So this is a way to calculate the panels for a system capacity of 9212 watt hour, unless this is a optional case. Here the 100% of load you can convert it to solar panel. It is little bit complicated for economic wise and easy maintenance wise and battery cost wise. Why this kind of problem means you are converted 100% purely to a solar panel. First thing, the number of panel is increased, so cost also increase. Battery sizing, maintenance and inverter problems, everything is available. So you can reduce the load up to some favorable amount. It is an easy way to run the solar panel over a year. So for that we are choose minimum 60% load is enough to convert it in the solar output. For that we choose 60% of annual energy, means you multiply with the total annual energy demand of 11,845 kilowatt hour with 60%, you can get that 7,107 kilowatt hour. So this is a 60% of annual energy demand. Then this value consider as a annual energy demand. For that you calculate the system size and number of panels. So 7,107 kilowatt hour in divide by 1,607 is your divide. You can get that 4.422 kilowatt hour is a PV system size for 60% of load. The system capacity is 4.422 kilowatt hour. For that 4.422 kilowatt hour, we need 19 panels of 232 watt. So compared with the actual load of 100%, we need 39 panel. If 60% of load is enough, means we need 19 panels. So cost wise it is efficient, and battery sizing is reduced, and inverter and all kind of maintenance is easy to operate. Now conclusion: for a double floor single family residential, we consider the 100% of load. The load is calculated 11,845 kilowatt hour, and identify the system size is 9.2 kilowatt hour. We need 39 panel. The same case, you are taking only 60% load is enough. That annual energy demand is calculated 7,107 kilowatt hour, and identify the system size is 4.422 kilowatt hour. Then we need 19 panels to achieve the annual demand of 60%. Now the conclusion: for the photovoltaic system calculated for a residential building is required 39 panels of 232 watts. That means each panel produce 232 watt output for 9.212 kilowatt system capacity, which designed and connected it operate and produce 11,845 kilowatt of annual energy demand. The same case, you are considered the 60% of load, means we need 19 panels. The 19 panels at 232 watt, which produce the 4.422 kilowatt as a system capacity, which operate 1607 per year. So produce the 7107 kilowatt hour of annual energy demand at 60% load. This is the way to calculate annual energy demand, annual sun hour, and system capacity, and choose the panel rating and sizing, and select the